Log on, tune in, find out. Another good idea from Cambridge.
Speaker is Jean Dolbeault from Paris-Dauphine, and Jean is going to speak to us on thermal effects. Please.
Thank you very much. Thank you very much for giving me the opportunity to expose this series of papers. So I have mentioned here actually 4 papers which were with Patricio Felmer, Michael Loss and Eric Paturel and other people, and the last one is with 2 former students of Peter, Gonja Aki and Christoph Sparber. So let me just very briefly say what is the contents of this paper and the purpose of my talk. So in the first one, actually the purpose was to understand how we can define some free energy functionals for some quantum systems and why it has to be bounded from below. So hidden behind this, there are functional inequalities which are interpolation inequalities and also Liptiering inequalities which are closely related. Then these inequalities also correspond to some compactness property. I won't have much time to speak of this. And this is very useful to study a system with mean field terms. And by this I have in mind Hartree Fock system for atoms and molecules with temperature, and gravitational models with temperature. So I will explain a bit later how the temperature enters in the model. We are actually building some very special solutions which are minimizer of a free energy functional and correspond to system at non-zero temperature. So let me just directly go to the first one and explain how Liptiering inequalities are playing a role in this. This is some already a bit old stuff, but it gives a clear light on why you can build functional which are bounded from below. Okay, so here is the general idea, which is actually rather simple. Imagine that you consider a Schrödinger operator with some potential V. So it's here in Rd, and here we can assume, for instance, that V is a negative potential which is compactly supported. So the Schrödinger operator has absolutely continuous spectrum plus eventually a certain number of negative eigenvalues. And if the lowest one, if it has a negative eigenvalue, you can ask the question how to control the eigenvalue here in terms of the potential. So this is a rather simple question, and actually what you want to do is get the best constant here, which allow you to control the negative eigenvalue, its absolute value, in terms of an LP norm of the potential. Okay, so this you can do by trying to find the maximum of this quotient for a smooth solution, or you can extend it by density to this larger space. Now, if you think how to define the first eigenvalue, actually you can insert the Rayleigh quotient, and what you are trying to do is to take a supremum in the terms of the potential of the supremum in all L2 function, actually H1 function, which define the Rayleigh quotient here. So the thing you are trying to maximize is this whole object, and you first observe that it has some nice scaling properties, in the sense that if you scale the function, if you scale the potential accordingly, then you don't change the value of the quotient. So now there is a formal game which is to intervert the order of taking the supremum, and if you optimize in V first, then the problem becomes essentially trivial, because you have that this linear term here can be expressed in terms, so when you make the variation with respect to V, you get simply U square. It can be expressed in terms of a power of V, that is exactly this power which shows up here, and it's convenient to introduce the power Q which is here, which relates both. So if you optimize first in V, you see that the quotient you have here will be bounded by T's with a nonlinearity u to the power 2q, which appears both on the numerator and on the denominator. Now, of course, once you have such a thing, playing with the scaling is natural, and what you get is an expression which is now homogeneous and scaling invariant after optimizing under scaling, and this is just the quotient which defines the Gagliardoni-Renberg inequality, one of them. Well, you have to be a bit careful with the supremum and the infimum, depends if you take the absolute value of the potential or the potential itself, but there is no big difficulty in this, and to justify this, it is no more than just the Hölder inequality. So the only thing you have to keep of this little computation is actually that the best constant when you try to control the first eigenvalue in terms of the LP norm, actually the L gamma plus d over 2 norm of the potential, is the best constant is actually related to the best constant of this more classical interpolation inequality, which is here, and this is the precise relation with a k2 which is given by this exponent. Okay, so that's the first observation. So this is something rather classical. Now, what you may observe is that this corresponds to, say, non-confining potential, in the sense that the potential V you want to consider is something which is essentially 0 at infinity. You may ask what happens when you have a confining potential, a potential which grows at infinity. And it turns out that you can do exactly the same computation, or almost exactly the same one. So what you do is you take a potential which grows at infinity, and then you denote by lambda 1, lambda 2, now the eigenvalues, which are all discrete, and you do it in the right space, you introduce an exponent, this is the same in computation, and you end up with the fact that computing the best constant in this interpolation inequality amounts to control the power law, but now a negative power law of the absolute value of the first eigenvalue in terms of a negative power of the integral of the negative power of the potential. So what we have changed here is that instead of having v going to 0, we have v going to plus infinity, and at the level of the interpolation inequality, we have exchanged the role of 2q and the L2 norm. Before we had the L2 norm on the denominator, and we were controlling the L2q norm. Now it's the opposite, but q now is less than 1. Okay, so everything is fine. And well, this is actually the result. So if you have a potential which grows at infinity, then you can control a negative power of the eigenvalue, which is now taken to be positive here, in terms of a negative power of the potential, because now I have gamma strictly bigger than d over 2. And again, this C2, this best constant which is here, is exactly equivalent to compute the best constant in another Gagliardoni-Renberg inequality. So now you have two families of interpolation inequalities. Now there is a case which is a limiting case for these two inequalities, and which amounts to take q going to 1, and this will be related to the log Sobolev inequality. So before doing that, I will just set this in a very general framework. Actually, if you have two functions, capital F and capital J, which are related by some Legendre type transform, computing the best constant in this quotient, where you try to control the eigenvalue in terms of an integral of the potential, exactly amounts to control an interpolation inequality, which is now slightly more complicated, which takes this form. Of course, if you don't have a power law, then optimizing and scaling is not as obvious as it was, but the general structure is still the same. So as a special case, for instance, you can be interested in understanding what happens when q goes to 1, so 2q goes to 2, so you have the same power at the numerator and the denominator, and actually what you get is that what shows up is the exponential. So what you would do in this limiting case would be to control an exponential of the first eigenvalue in terms of the integral to e to the minus v. Okay, so this is at the level of the Schrödinger operator for a confining potential. And if you look at the corresponding interpolation inequality, well, you just recover the logarithmic Sobolev inequality, which is a nice limiting case. Okay, so far not so much is new. And actually, so this is the equivalent form when you control e to the minus lambda 1 of v in terms of the integral of e to the minus v, and it is exactly equivalent to the case of the logarithmic Sobolev inequality. So the question of computing the optimal constant in such inequalities is not that hard. This can be done, and in that case you control everything. You can do the computation. Now, of course, this is not what people call the Liptier inequality. The Liptier inequality, you want to control a whole series of power laws of the eigenvalues. And well, the observation that we have done here is that actually it is amounts to have some interpolation inequalities for system of orthonormal functions. So let me just explain first what is the standard setting for the Liptier inequality. You have a potential, which is again a potential which is smooth, going to 0 at infinity, eventually compactly supported, and you have a finite number of negative eigenvalue plus eventually some positive continuous spectrum. And the gain is to control such a series with a positive power law in terms of this LP norm of the potential. So here this is a much more difficult question, and actually the optimal value of this Liptier constant is not known for arbitrary values of the exponent gamma, which is here. However, there is a way of rephrasing this in terms of interpolation inequalities for system. Now, what is nice is that you can also play with the negative powers and get an optimal constant, an inequality where you control the sum of the negative powers when the spectrum goes to plus infinity, which corresponds to a potential growing at infinity, and in that case you have this with the explicit form, which is here. Okay, so this is the inequality that will be, well, one of the inequalities which is of interest, and I will show you a bit later how you interpret this in terms of interpolation. Well, to compute the optimal constant is not such a big deal. Actually, it is an explicit computation, but I don't want to spend so much time on this. It is something which is rather standard using the Golden, Thomson, and Sinancic theorem. Okay, so actually it is as a generalized form, and actually for any function f, you have by some transformation associate some capital F and capital J, which are given here. And with this transformation, which is explicit for odd dimension, if I remember well, but not explicit for odd dimensions, you are able to control a sum of the function of f of the eigenvalues in terms of such an integral. So this is valid for an arbitrarily large number of eigenvalues. So there are some cases where, again, it is explicit. So we have already seen that if we take a negative power, then this can be computed, and this is the expression of J of S. And this can also be done in the limiting case where you take the exponential. So you have this nice summation of eigenvalue formula, which tells you that the sum of the negative exponential minus the eigenvalues go to plus infinity, is controlled by e to the minus v, which is something which is rather nice. Just notice, by the way, that actually the first eigenvalue is the one which counts the most. There is only a discrepancy of a factor 2 over e compared to the case where you were just minimizing or optimizing with respect to the first one. So actually, it is just the first that counts essentially in this. Okay, so how can you use this to understand something about Schrödinger equation? And the goal is to understand what happens for mixed states and how you can build a free energy, which should be a convenient tool to understand the stability properties. So first, let's fix the potential V and consider the Schrödinger energy, which is here, and actually the eigenvalue associated to this Schrödinger operator. So the eigenvalues, well, they are defined by these Rayleigh quotients, which are here. And if you associate an orthonormal sequence of eigenfunctions, so think to the case where V goes to plus infinity, then we will define the free energy of a mixed state. So a mixed state is a sequence of occupation number and a sequence of eigenfunction within that form as an entropy term, which is here. Here temperature is taken equal to 1, but it should be multiplied by the temperature if we want to vary the temperature, plus the energy, but notice that the energy corresponds to the energy of each eigenfunction multiplied by an occupation number, which is here. Okay, so of course you have to make some assumption on what is the function beta here, and it's very natural to take some strictly convex function beta, but well, I will comment on this a bit later. At least the kind of assumption you have to make for the whole thing to make sense is that if you take the eigenvalue of the Schrödinger operator, which is here, and compute these optimal occupation numbers nu I bar, which are here, then these two sums make sense. So actually we want to work in a setting where this quantity is finite and this is actually the right setting. Yeah? Okay, so why do we want to use such a thing? Well, first, if you make the difference of this free energy here for an arbitrary sequence of occupation number and an arbitrary sequence of orthonormal functions here, with the optimal one, and we will see that the optimal one is made of the eigenfunction with occupation number corresponding to the eigenvalues, then actually you can rephrase it in this form, and this term turns out to have a sign. So what does it mean? Well, here you see that if you have a convex function, this is just a Taylor expansion at order 1 around nu I bar, the sequence nu I bar. So this actually controls some distance of the nu I to the optimal occupation number nu I bar. So this can be made precise. So this is a kind of Caesar-Kullback type inequality, which tells you that this difference here actually controls a norm of the distance in the sense of the sequences of nu minus nu bar, of course provided you made some assumptions, and the assumption that you have to make is that essentially beta of s behaves like a power with a power law, like with a power between 1 and 2. Okay, so notice for instance that it contains the case p equal to, this term simply drops, and that corresponds to beta of s equal s square, so you would be in the L2 framework. This contains all power laws for p between 1 and 2, and the limiting case when p goes to 1 would be beta second equals 1 over s, that is the logarithmic case, so beta of s equal s log s. So p equal 1 is actually covered by this example, and the Caesar-Kullback inequality, properly speaking, corresponds to the case p equal 1. P equal 1, beta of s is s log s, and this quantity just controls the L1 norm of the difference here. So why are we interested in controlling such a quantity? Well, actually the occupation numbers tells you how you populate states so how you put some weights in excited modes of the Schrödinger operator, and what this quantity tells you, or this free energy tells you actually, is how far you can be if you are close in free energy of the minimizer. So asymptotically it means that when you take a sequence nu n and psi n converging to the minimizer, the occupation numbers have to go towards the optimal ones. So here everything is done at 0 temperature, but then we will play with the temperature a bit later. Okay, so let me go to some examples to make this a little bit more clear. Again, we will find these two families of interpolation inequalities, the one corresponding to q bigger than 1 and q less than 1 that we had for the Liptian inequality, and as a threshold case, you recover the logarithmic sub F case. Okay, so first case is the case where you take a power nu for the, so beta of nu is nu to the m and m is bigger than 1, so it's the classical convex case of power laws. And you see that when you optimize, you can relate the capital F, which shows up in the inequality, with the beta of nu. Well, actually capital F is exactly the power law, so you recover the setting of the Liptian inequalities. Well, you don't recover all exponents, and there are some limitations, but at least there is a range in which we recover the classical exponents of the Liptian inequality. Now there is another case that you can study, which is the case where m is less than 1 with a negative sign. So nu to the m would be a convex function of nu, but if you put a negative sign, again this is a convex function, and then the whole thing works, and actually that's how you recover the negative power law for in the inequalities. And then come the limiting case between these two families of inequalities, and that's how you recover this e to the minus lambda I of v in terms of the integral of e to the minus v. In that case, everything is simple. Capital F and capital J are just exponential with some coefficients, and that's it. But you can also deal with other cases, and for instance, when you are interested in models in which you involve some fermions, you want to have the limitation of the occupation number to be between 0 and 1, and then instead of nu log nu, it's very standard to take nu log nu plus 1 minus nu log of 1 minus nu, and this gives rise to, for instance, such an inequality, and again you can compute the optimal constant. So what's the game of all this stuff? Well, actually, the right object to study is the free energy. And it's exactly like the computation I have shown to you at the beginning. You write the free energy, you can fix the potential and minimize with respect to the occupation numbers and the wave functions. In that case, you end up with the Liptering inequality, or you can do the opposite. You can optimize on the potential in terms of the wave function, and then you get the nonlinear interpolation inequalities. Now, what is interesting is to have this free energy bounded from below to use it for stability results, and this is actually something which is given, for instance, by the Liptering inequalities. Okay, so what does it mean, Liptering inequalities for systems? So I have rewritten the inequality which is here. Now, if you think in terms of the potential, well, you have all these relations. I don't want to insist too much, it's a bit technical. And if you write it at the level of the free energy is this quantity. So T is just the energy of the Schrödinger operator multiplied by the occupation numbers. Here it is the entropic part. And when you use the Liptering inequality, what you get is that this whole quantity is non-negative. So now, just to show you that we have really extended interpolation inequalities to system, I will go to the end of the logic of optimizing with respect to V. If you do that, well, you have to make the variation in this with respect to V. You get something which is explicit of V in terms of the density, the spatial density, which is written here. And using once more a kind of Legendre-Fenchel transform, which is here, you get that optimizing in V means that you have this, they will combine in this form. So if you replace V by the optimal form, which is here, by combining this term with this one, the interpolation inequality you get is this one, where K is just the kinetic part, so the sum of the nu I gradient of psi I square plus the entropy term control some nonlinear functional of the density. Okay, so this would be the general interpolation inequality for orthonormal system. Okay, so let me show you on the example what it means. It means that if you have a control on the kinetic energy part of this mixed state described by occupation numbers and orthonormal wave function, plus some information of the entropy term, then you control an LQ norm of rho. No? Okay, and the explicit, well, you can even optimize under scaling, and you get an expression which is really of Gagliardoni-Renberg type. At least if you take nu1 equal 1 and all the other 1 equal to 0, it is exactly the Gagliardoni-Renberg inequality I have shown to you at the beginning. So this is the first class of inequalities where you control the LQ norm by the L2 norm. The L2 norm is hidden in the fact that the psi I are normalized in L2. Huh? Okay. You also have the opposite case where you take Q less than 1, if I'm not wrong. Yes, Q less than 1, and then the combination of the entropy term the kinetic part plus this LQ norm of rho controls the entropic term, and you have the limiting case where you have the analogous of the log sub F inequality for systems now, which means that this density, which is made of the combination of all these wave functions with a weight corresponding to the occupation number, actually is controlled, or actually rho log rho is controlled in terms of nu I log nu I plus this kinetic energy term, which is here. Okay, so this is the first tool that I wanted to expose here, and this is how you can get some a priori bounds on the on the free energy, which tells you that this is a well-defined quantity to study, for instance, stability properties for the evolution problem. Okay, so I will skip this part. Hidden behind these inequalities, you have also some nice compactness properties which can be made completely explicit, but I don't have time to explain this. Let me just do this and go to the first application, which would be for Hartree-Fock, the Hartree-Fock theory in case of electrons, so the case of quantum chemistry. And here, well, the game would be, in some sense, to understand what happens for a heated atom. So what you want to compute is an excited state where the wave functions are not all in the lowest possible state, but they are distributed in the excited levels, and you want to optimize the free energy. Okay, so let me just mention that there was this paper which has been a source of inspiration in a slightly different context of Schrödinger-Poisson systems, so more oriented towards semiconductor physics. And what I'm going to briefly show is the result that we have obtained here. Of course, this is where the interesting thing come in, because you will see that when you introduce temperature, then you can eventually see some new physical effects, and that's the interesting part of this approach. Okay. So let's consider the free energy. So the free energy is made, like before, of two pieces. The first part is the Hartree-Fock energy here acting on the density operator, which is another way of writing these mixed states. And you have the entropy multiplied by the temperature, and here I took the physics convention, so with the minus sign here. Okay. So if you look at physics textbook, actually, usually you find that the entropy is only generated by the function beta of nu is nu log nu, or eventually nu log nu plus 1 minus nu log 1 minus nu. And in that case, due to the fact that we have a potential in the Hartree-Fock theory which is not confining, we immediately hit a difficulty. The free energy is not bounded from below if you take such a free energy. So there was an old paper of Pierre Williams that he wrote when he was studying the Hartree-Fock model at 0 temperature, and actually he mentioned that if you take simply nu log nu, there is no way to bound the free energy from below, and it's not even clear how to get critical points or whatever. Of course, it is as long as you are in the Hull space. If you are in a container, if the system is confined, then there is no more problem. And actually, this was studied in this paper here. Okay, so what is the goal of this? The goal of this would be, well, to say, okay, we cannot do the theory for nu log nu, but we can eventually do it for some other convex functions, and actually this turned out to be the case, and there is a whole zoology of models for which you can do it, and exponents are going to play a role. Okay, so before going to these details, let me mention that we are working with fermions, so we want to have a function which is supported in 0, 1. We want to have it infinity away from the interval 0, 1, so this is not a big deal. And for the Hartree-Fock energy, well, we take the standard case, so you have the kinetic energy term, which is here. You have the potential here, it's written in the atomic case, but there would not be so much difficulty to extend it to the molecular case. So here we simply have one atom with a singularity and a nucleus with positive charge Z here, which is attracting all electrons. And then you have the two nonlinear terms which are standard in the Hartree-Fock approach. One is the direct term, which corresponds to the self-energy of the electrons with themselves. And then you have the exchange term, which appears in the standard way when you derive the Hartree-Fock energy from the Schrödinger energy for n-particle system. Okay, so this is the energy, and I don't want to spend too much time on it. Okay, and let me just mention that the evolution equation is this von Neumann equation. You can also write a system of Schrödinger equation, but one has to be a bit careful here. If you are working at 0 temperature, then actually only a finite number of eigenfunctions are involved, the lowest energy levels. and this is fine. And actually, the system is not so much nonlinear. The coupling just comes from the fact that each wave function sees all the other ones but doesn't interact with itself. So it's just a slight modification of the linear theory, and actually it is very important because you want to know what are the energy level of the linearized operator, but this linearized operator turns out to be actually like the Schrödinger operator that each wave function sees. Okay. Okay, so the evolution problem, I prefer to write it at the level of density operator, and this is like this because we are going to consider now cases where you have infinite sequences of occupation number, and this turns out to be a simpler framework. So one of the questions you want to ask is, can you get some stability results of a solution, in the sense that if you start with an initial data which is low in free energy, does it stay close to the minimizer of this free energy? And the answer is going to be yes, and it's actually something which is non-trivial, because along the evolution you may have crossings of the pseudo eigenvalues. Okay, anyway, I was anticipating on what is going to be said here. So as before, we want to have an entropy generating function which is strictly convex, so there are a certain number of assumptions that you want to do. Let's take it C1 with this condition to simplify a little bit the things. Well, of course, you have in that game you always are doing Legendre transform up to a sign, so you always consider this. This is what is going to appear when you optimize the entropy term, when you fix the occupation numbers. Okay, and well, there is some beta star which is here. Anyway, forget about this. And you have two additional assumptions. Here, the fact that you can, well, take a zero derivative, this is not a big point. In all this approach, you want to optimize with a fixed mass or a fixed number of particles, so you can always remove a constant times the mass. So imposing this, as long as beta is differentiable in zero, is no problem. Okay, and then there is a more technical assumption which essentially tells you that the contribution, when after optimizing on the free energy, if you just take the eigenvalues which are given by the Coulomb singularities, well, the contribution will be finite. And this is something which is crucial, and actually understanding how it enters is something which is not completely understood. I will come back to this. Okay, so again, well, the typical example you can take is not nu log nu, but nu to the power m, and you will see that the power n equals 3, dimension 3, plays a special role. Okay, so all I'm going to say is in dimension 3, the physical space. Okay, so you have to define properly these quantities. Well, this is the quantity I've shown to you before. This is nothing else than the lambda to the power gamma that we add in the Liptian inequalities. Sorry, this beta star which is here, sorry. And you have to work on the convenient space, well, the space on which everything is well defined, actually in which the kinetic energy part is well defined, and which correspond to trace class positive operator with given mass. So the constraint on the mass is going to come soon, no, maybe later. Once you have done that, if you take the natural norm, which is this1, everything is well defined. Actually, we are not going to work on this whole space, but since we deal with fermions, with electrons, we are going to impose that the density matrix is between 0 and 1 in the operator sense. So we work on this convex set, and then everything is fine. So of course the kinetic energy is well defined. You can define the density of charge, well, formally in that form, and we are going to impose that it's in L1. Actually, the integral of the spatial density is going to be the mass. And well, it's not very hard to see that the square root of the spatial density, the gradient of it, is controlled in L2 by the kinetic term, so everything is fine. We are in a nice space. By the Sobolev embeddings, we know that rho gamma is going to be contained in this. And T space L1 and L3, the intersection of L1 and L3 contains L6/5. L6/5 is the power you need to use R-Delitter with Sobolev inequalities and to control the terms which involve the Coulomb singularity. Okay, so this is what is done here by Hartree with Sobolev inequality. Everything is fine. You control the exchange term, and there is no problem. So far, so good. So the question we are interested in now is to, on this convex set with a fixed total charge for the electrons, to understand if we can get a minimizer of the free energy under this constraint. So actually we have two quantities, the first quantity which depends on the charge, which is here, and eventually this quantity which is the infimum on all possible charges, and we will distinguish whether they are equal or different. Okay, so here we have the general setting, which is based on the theory of concentration compactness, and there is not such a big deal in adapting what has been done by Pierre Williams long ago. And well, we have that a minimizing sequence is going to converge up to the extraction of subsequences if you have some kind of binding inequality, and this binding inequality just tells you that you have an amount of electrons, a number of electrons, a charge of electrons which is not too big, so that you are still in the regime in which the infimum decreases when you increase the charge. Okay? And there will be a limitation eventually when this becomes constant, and then the method would fail. This would be the mechanism of loss of compactness, actually. Okay, if you have a minimizer, then it satisfies the cell-consistent equation. And there are cases, if you put too much charge, you know that you cannot bind the system, so there is no minimizer. The minimization problem has no minimizer. Well, there is a bound which was given by Lieb, I think, long ago, and which can, in some cases, be improved, but I think it's the only general bound. Actually, what you expect is that you cannot bind more than z plus 1 electrons in such a system. Okay. Okay. And now, the problem which is here, as always, a minimizer, but remember that this I beta z is the case where it doesn't depend on the charge. So you don't know how much charge you can bind. So of course, what we are interested in is understanding how many electrons you can bind. And the physical effects you are expecting is that when you start to hit, you start to populate the excited levels, then the higher is the temperature, the less you can bind electrons. So there is a kind of maximal charge that you can bind, and this is the physically interesting effect. To a large extent, it is still something which is not completely understood, but at least we have the basics for understanding this. Okay, so to understand a bit better what is going on, we have to go back to the linear case, and actually to consider the case where you just have the Coulomb singularity, and then you know everything. You know the spectrum of the Schrödinger operator, which is behind this. The eigenvalues go like 1 over g squared, and you know the multiplicities of them. And so you see, here it is the analogous of the free energy where you have removed the nonlinear terms. Okay? Once you have done that, well, you can compute what would be the total charge associated to this system using the fact that, well, actually you know what is the optimal density operator. Okay? And, well, it is a bound on the maximal charge, which eventually is infinite. Okay? But it can also be finite in some cases, and this is going to be the interesting case. Okay, so for this linear operator with just the Coulomb singularity, well, you get that the optimal density operator is of this form, and here we have had the two objects, the temperature and chemical potential, which is the Lagrange multiplier when you associate a mass constraint. So there are plenty of properties. I don't want to be too long. It's a bit technical. You have some decay property, for instance, of the charge you can bind. You get in for this density operator. It's something which is decreasing in terms of the Lagrange multiplier, non-decreasing in terms of the Lagrange multiplier. And then eventually you know that you reach the limit when the Lagrange multiplier goes to 0. Okay? So Lagrange multiplier going to 0 means that you go to a limit where the minimizer is going to have, in the limit, an infinite number of occupied states. Okay, at the level of the density operator, it means that the rank goes to infinity. So actually, here there is some zoology because it depends on the kind of entropy with codes function you take, and the linearized maximal charge you can bind can be computed, and depending whether m is between 1 and 5/3 or between 5/3 and 3, then you have two cases: this is finite or this is infinite. Okay, so actually this is well, I don't have time to explain this with full details, but this explains how you the linear problem enters into the game. You use it for getting a priori estimates on the nonlinear problem, and this gives you a criterion to know whether or not you have a negative value for the minimum of the free energy for a fixed charge Q. Okay, so first of all, if the charge of the nonlinear system is bigger than the bound which is given by the linear problem, then you already know that you have no minimizer. So if you put too much charge, no way you can bind it in that way. And remember that this quantity depends on the temperature. On the other hand, if you have this, then you satisfy the binding condition in theorem, which tells you that the infimum is a strictly decaying function of the charge, and by knowing that, you know that you can bind the state. Of course, yeah, okay. So I don't want to spend much more time on this. Well, the conclusion is that for a finite positive temperature, there is a maximal charge you can bind in such a system. This maximal charge depends on the temperature, and actually the precise dependence in the temperature is not something which is known. So this is actually some kind of ionization threshold, which is here, and it would be of very much interest to compute it, and this is not something easy. It is not something easy because you have to compute excited states, and you have to compute them accurately, and this is a difficult task. Okay. So actually there is an ongoing project, and Gaspar Jankowiak is involved in this, and the question would be to get some ideas of, for instance, how the ionization threshold depends in the temperature, and you cannot directly adapt the cause of quantum chemistry for computing Hartree. There is a numerical issue there. Okay, so now let me go to the last part of my talk, and maybe I will enter a little bit more into the details. So this is a model for bosons. So for this reason, we just dropped the exchange term in the Hartree functional, so it's actually just the Hartree functional, but we want to see how things depend on the temperature. So here we will change a little bit the setting. We don't want to fix the charge. Here we have particles which are bosons, which are not charged. We fix the total mass, and we want to see whether or not, depending on the temperature, the system can be bounded, and if it's bounded, if we can say something about the rank of the density matrix. And actually there are some interesting phenomena which appear in this. Okay, so this is a joint work which has been recently submitted with Gonja Aki and Christophe Spaber, who is maybe in the room. Yeah. Okay, so let me recall you a little bit what is the setting. So you consider the space of the operators from L2 to L2, which are self-adjoint, which have all good properties, which have definite kinetic energy, and you equip it with T's norm. And what we are interested in is trying to minimize a free energy which is of the same type as before. So here you have the kinetic energy term. Here you have the self-consistent Poisson term, but with the attractive sign, and we drop any exchange term, there is no point here, plus a temperature, time and entropy term, up to signs depending on the convention you choose. So you see what is going to happen is that at 0 temperature, such a system is known to have a minimizer, which is rather simple. It is actually a pure state, and when the temperature increases, this term starts to increase. So of course there is a equilibration. You want to minimize this, and to minimize this usually you want to distribute the occupation number on a large number of states. But of course this is not energetically favorable here. So there is a competition between these two terms. This is what is the physical aspect. So the game will be to understand how this competition takes place and who wins depending on the regimes. Okay. As before, well, as I told you, sorry, you want to fix the mass and see how things depend on the temperature. Actually, it is not such a big deal. You could also fix the temperature and look for a kind of critical mass, but since in the astrophysical context there are other meanings for critical mass, I prefer to fix the mass. Huh? Notice here that for to simplify a little bit the setting, we take an operator which is a non-relativistic one. Of course, for stars it makes a lot of sense to have a relativistic operator, except that well, people usually use square root of 1 minus Laplacian, which is not that physical. But anyway, so here we drop all relativistic effects to concentrate on the effects directly linked to temperature, because it is a slightly easier setting. Okay, so first you have to check that everything is well defined. Actually, at this level you don't need the interpolation inequalities or the Lipschitz inequalities, because you can directly control the nonlinear terms in terms of the kinetic energy. And actually, by the Hartree-Sobolev inequality, you see that this is a Poisson term, which is here, where n rho is the density associated now to the density operator rho. Sorry, I've changed the notation compared to the previous section. Okay, it is well, this density is controlled by some L6/5 norm, if I remember well, and this you can interpolate between the kinetic energy and this norm. Okay, anyway, plugging all these estimates into the energy, the Hartree energy, so corresponding to 0 temperature when you have no entropy term, then you see that you have a kinetic term plus a potential term which is bounded by the square root of the kinetic term, so you can minimize this and get a bound in terms of the mass. This is rather standard. Now what you want to do is to add this entropy term, so minus Ts, so it gives a term which is a positive contribution to the free energy, and you want to see whether your infimum is still negative or not. Okay, so so the free energy is just the combination of of the Hartree energy at 0 temperature, which is here, plus T times S, and with this, in this setting, everything is well defined. Okay. So now, as usual, in this concentration compactness method, you have to you look at a minimizing sequence, and you want to decide whether it converges or not up to the extraction of subsequences. So just a compacity argument. The key argument for this is to understand how you could lose compactness, and the standard mechanism in such subcritical system would be the splitting of the system into two subsystems. So the first estimate you need to have is that that when the system splits into a subsystem with mass m and mass capital M minus n, you have an inequality which is here, where this is just something you can reach by a direct estimate. You split your operator in two operators which have disjoint support, and if both of them are almost minimizer of each part, then you get an estimate on the combination of the two. Now, if you have equality in this inequality, then you are in danger of loss of compactness, and this may happen at positive temperature. So, if you want to prove the compactness, you have to prove that when you have two subsystems, actually they interact and they get binded, and this is why you get the existence of a minimizer. Okay, so there are some properties which require a little bit of thought, but it is nothing difficult, and so I won't insist on this. And now, well, you have to be a bit careful on what happens with the entropy term. So the behavior at 0 will be crucial. Behavior at 0, remember, it's when the occupation numbers are small. So this is this behavior that decides when you have more and more when the rank of the density operator increases, which would correspond to the asymptotic of large temperature. So actually what you can prove is that if your function beta, which generates the entropy, grows faster than a cubic nonlinearity, is it correct? Yes, right? Then actually, yeah, this is what is written here. Then there is no problem. T star, the maximal temperature for which you have a negative infimum, is going to be infinite. But this is not granted in general. So you have cases where this temperature may be finite, and we will see some examples. Okay, so if you have a minimizer, it's not a big deal to see what is the shape it has. It takes this form exactly like we had before in the quantum chemistry case, with mu Lagrange multiplier, which has to be adjusted in order that you have the mass constraint. Okay, and actually you can compute this by this formula. Well, this is just actually writing what are the occupation numbers and summing them. Well, okay, this is how you translate it in terms of mixed state. So if you represent your density operator rho as the sum of the projectors on the state psi I with eigenvalues lambda I, then get a spatial density, which is this quantity here. Okay, for a minimizer, they have to solve they have to be eigenstates of the Schrödinger equation, this one, where actually the potential is the nonlinear potential, so this is a nonlinear problem. The occupation numbers are just given by this, and when you sum them, you have to find the mass, which is the constraint that determines, in practice, the Lagrange multiplier. Okay. Now, assume that you are in the regime where the exponent of the function beta close to nu equals 0 is less than 3, and then you can show that the Lagrange multiplier is below the value of the infibum, so it cannot go to 0. But okay, let me be brief. Okay, so you have a nice relation which allows you to study what happens when the temperature increases. Now you are in a case where T star, the maximal temperature for which you can bind the system, can be finite. Okay, so what can you do when you want to minimize? Well, what you have to do is first to get some estimates which tells you that the system stay concentrate. So this is an estimate which looks standard, but actually when you go to numerics, it is apparently something which will be very hard to control. Indeed, when you look at the self-attracting system, the system has, well, the potential is given by the convolution, and there is no singularity corresponding to the Coulomb singularity that we had before. So the system is much more spread, which means that the wave functions are going to be less concentrated, and actually getting an estimate of this constant is an issue when you want to do numerics. Actually, we don't know how to do that. Now, if you look at the concentration compactness method, to get the compactness of the minimizing sequence, you need to have the strict binding inequality, which means that you prefer to bind two subsystems instead of putting them far apart. Okay, and so this is the inequality which is stated here, and here there is another main difference with the repulsive case with a Coulomb singularity, the quantum chemistry case, is the fact that if you have you have the inequality provided you have minimizer for each of the two subsystems, but this is not granted, because if the mass of the subsystem becomes small for a fixed temperature, you are not sure that you are going to have something which is bounded. So here the analysis is a bit more delicate, and then one has to be careful. Anyway, once you have solved these new difficulties, the existence of minimizer follows from the usual theory, and you can prove that there exists a positive temperature T star below which there is an optimal function for the minimization problem. Okay, so yeah, this is the standard approach. In terms of orbital stability, it tells you that you have a way of measuring how a solution of the Cauchy problem for an initial data which is not a stationary state is going to stay close to the optimal function. And that's quite interesting, actually. Probably from a mathematical point of view, it is maybe the most striking aspect of the result. The fact that if you are close in free energy of any given stationary state, whatever the free energy is, then you stay close along the evolution. Which means that with the distance which is induced by the free energy, okay, you stay close, the sequence of occupation numbers stay close, whatever the wave function do along the evolution. And remember that this is a nonlinear problem. Okay, so this is the orbital stability result, which is otherwise something rather standard. Okay, now comes another question. If you look at the problem at 0 temperature for the Hartree model, okay, then it's known for, since the work of Elliott Lieb in 1977, that actually the minimizer is achieved by a single wave function, a pure state, in the sense that the density operator is of rank 1, it's just a projection onto the lowest, well, this psi naught, which just solves a Schrödinger-Poisson equation, the Schrödinger-Poisson equation, which is here. And actually, a lot of things are known, for instance, on the eigenvalues and how they grow. Okay? Well, what happens here is that we have exactly the same phenomenon if the temperature T is small. There is a positive critical temperature below which the system is in this pure state. Okay? Of course, the value of Tc depends on the free energy you take. Huh? Okay. So you can be a bit more precise, and actually there is a complete characterization of this critical temperature because you have enough information on the spectrum of the Schrödinger operator corresponding to the potential given by the pure state. So by contradiction, you can first show that this temperature is strictly positive, and then by doing a slightly more detailed analysis, you get that the expression of the temperature here is given in terms of the eigenvalue of the Schrödinger operator divided by the derivative of beta in terms of n. Actually, the right way to see this is just, well, to look at the okay, maybe okay, right, that the Lagrange multiplier, as long as you are in a pure state, is explicit. What do we have? Well, we have the energy with occupation number 1 corresponding to the lowest energy level, so the pure state, plus the entropy term, and in the entropy term you just have the occupation number, m equal with, I should have written it with m here, sorry, there is a missing m here, or take 1 here. And yeah, so this, okay, sorry, no, sorry, it is correct. Huh? Actually, this is what happens when you optimize the free energy with respect to nu1, all the other nu i's equal to 0 for a pure state. Okay. Okay, so then this allows you to compute mu in the Lagrange multiplier in terms of the temperature, and as long as the Lagrange multiplier is below the second eigenvalue, mu1, 0, then you are in a pure state. So by putting this term on the other side and dividing by beta prime of m, you get the expression of the critical temperature. Okay. Now let me conclude by just mentioning that there are cases in which the maximal temperature for which you can bind the system is infinite. There are also cases when P is below 3 in which the maximal temperature is finite, and actually the case where P is between 7/5 and 3 is mostly open. Okay, so I'm going to stop here and thank you for your attention.
Questions, comments? Based.
Yes?
Okay, so as you said, here's the non-relativistic gravitational case studied.
Yeah.
In particular, because in the pseudo-relativistic, when you replace, Laplacian by
Square root of 1 minus Laplacian, yeah, right?
there is this extra constraint, mass constraint.
Yeah.
But what would you expect that where sort of this mass constraint sort of, if you would do the same for this pseudo-relativistic thing,
Yeah. So
where would it be? Would it be
Okay.
above the critical temperature for the mixed state, but below the T?
okay.
I mean, of course, we frame.
Yeah. So okay. So the Chandrasekhar theory is the following: you have an operator for the kinetic energy, which is essentially of order 1. So it scales like the Coulomb singularity. So then the mass is a critical parameter. So if the mass is too big, 1.3 times the solar mass typically, then the potential energy terms wins over the kinetic energy term, and then you have collapse. So it's a completely different phenomenon. Okay, so here part of the game was not to take the relativistic term to get rid of this difficulty, of course. Yeah, I have to think a little bit about the scaling. There is a scaling in which you can fix the temperature and play with the mass, and it needs some thought to see where it locates. But there is a regime in which you get an instability because just the potential term would win, and I don't expect that there will be so much new compared to the theory at 0 temperature. But it is to be checked. Yeah.
When you think of this critical temperature, and when you think in terms of the occupation numbers, there must be some kind of bifurcation out of 0, right? I mean, you go from a pure state to a mixed state.
Yeah.
So what I mean,
so the mechanism, okay.
The
The picture is that probably the spectrum, when you linearize when you linearize around the minimizer, you get the Schrödinger operator where you freeze the density in some sense. Huh? Okay, the Schrödinger operator corresponding to this frozen density. And then these are the spectrum, which is discrete. Eventually it accumulates at 0. Okay? And what you expect is that for small temperature, this spectrum, when you increase the temperature, moves continuously. Okay, at least the really negative eigenvalues, the strictly negative eigenvalues, the eigenvalues which are below minus epsilon. Okay, and then the Lagrange multiplier would then move continuously. So what will happen is that the rank of the density matrix will increase each time it crosses an eigenvalue. Of course, the rank will increase with the multiplicity of the eigenvalue. That's what you expect. And numerically, we have some indication, and Gaspar has some result on this, where you see that you get 1, then, okay, you have the pure state case with rank 1, and then you cross the first eigenvalue and you get rank 2, and then it increases. Now, when you reach the maximum temperature, then it is another game. Either it means that that the Lagrange multiplier goes to 0, and this would correspond to p less than 3, I guess. Yeah, I think so. Or p is larger than 3, and then the infimum of the energy increases, and also the Lagrange multiplier, up to a regime where you cannot bind more mass, because this mass just evaporates, in some sense. So, which means that the infimum, when you minimize for fixed mass, how to say, yeah, you lose compactness in the sense that the system split, only part of the mass would remain confined and the other part would evaporate. But this has to be checked, and we have to be a bit careful with this. This is some heuristics.
Complicated mechanism.
Yeah, there is something to understand there. And of course, it will be extremely hard to investigate numerically because you want to go to high rank matrices.
Okay, if there's no more questions, Christoph? Ah, no.
Yep.
Okay. Well, then let's thank Jean.